Hello, everyone. Welcome. My name is Jennifer Nyman. I'm a senior principal at Geosyntec Consultants in Oakland, California, and coordinating the webinar series on behalf of SERDP and ESTCP. I will be facilitating today's event. This webinar today focuses on DoD-funded research efforts to develop technologies to prevent corrosion on DoD components. First, Dr. Isaac Nault of the U.S. Army Weapons and Materials Research Directorate will present on his team's evaluation and demonstration of a series of cold spray coatings to replace chromium and nickel plating. Second, Mr. Greg Liscombe of the U.S. Air Force Sustainment Center and Mr. Casey Jones of ES3 will discuss the demonstration and validation of a low hydrogen embrittlement alkaline zinc-nickel electroplating system as a cadmium chromium plating alternative at an advanced metal finishing facility. Each of these two presentations will be followed by a brief question and answer session. And then we're going to conclude the webinar today with a final Q&A session with all of our speakers. The next few slides provide some instructions for your webinar experience. If you haven't done so already, you can download Zoom at the link shown here and provided to you in your registration email. If you can't download Zoom, you can still view the slides using an internet browser and by creating a free Zoom account. If for some reason your screen freezes, you can try keying in Control with the F5 button on your computer to do a hard refresh. For audio issues, if you're accessing audio through your computer, you can click on the arrow next to the Join Audio button to select Test Speaker and Microphone, and then follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here. You can also submit a comment using the chat box in Zoom, but please use that chat box just for comments related to technical difficulties. We're going to use the Q&A box to have questions for the speakers. And in case of continued technical difficulties, you could always download a PDF of the slides for today from the SERDP and ESTCP webinar webpage, and then you can call into the conference line given to you in your webinar registration confirmation email. Finally, we will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast is listen only. Please submit questions for the speakers. You can do that using the Q&A box on your screen. And you don't have to wait until the Q&A period to submit questions. It would be great if you sent in questions even in advance of that session. And when you submit a question, please add your name of the organization that you're with to the end of your question. And with that, I would like to introduce Maya Rabinowitz, who is a Weapons Systems and Platform Specialist at Nobles and the Technical Assistant for that program area in SERDP and ESTCP. She has worked with SERDP and ESTCP since 2020. She received a bachelor's degree in environmental biology from Georgetown University and is pursuing a master's degree in biotechnology with a biodefense concentration at Johns Hopkins University. Maya.
Thank you, Jennifer. I'm happy to welcome everyone to today's SERDP and ESTCP webinar. The next few slides will provide a quick overview of SERDP and ESTCP. SERDP is the Strategic Environmental Research and Development Program established in 1991 by Congress as a partnership between the DoD, the Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities that focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program in which we demonstrate innovative environmental and energy technologies. These investments capitalize on past investments under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the ultimate transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring at the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are several environmental drivers for the type of work funded by SERDP and ESTCP, with the underlying objective of sustaining DoD ranges, facilities, and operations. This, as you can imagine, is a broad undertaking. It takes the form of looking at maritime sustainability, threatened and endangered species, climate impacts, unexploded ordnance and munitions constituents, as well as other environmental drivers. One key environmental driver is the reduction of current and future environmental liabilities. This involves addressing contamination from past practices, including impacts to groundwater, soils, and sediments, UXO contamination, and developing management approaches for contaminants of emerging concern. The second part of this is pollution prevention, with a focus on eliminating chemicals of concern or hazardous materials in manufacturing, maintenance, and operations on our installations. We have several main focus areas for research and demonstration at SERDP and ESTCP, which are shown here. As mentioned earlier, technology transfer is particularly important within the SERDP and ESTCP programs. Technology transfer efforts include the development of videos, training workshops, and guidance documents. The webinar series is a substantial component of our technology transfer efforts. Our webinar series highlights research and demonstration efforts from all of our program areas. Upcoming topics include conservation efforts for managing populations of threatened and endangered species, enhanced sensing for detailed surveys for munitions detection and localization in very shallow water, and forensic methods for PFAS source tracking and allocation. Registration is open for webinars through the beginning of next year. You can find additional information about upcoming webinars at this link. All past webinars are archived and can be accessed using this link as well. Please note that the 2023 symposium will be held between Tuesday, November 28th and Friday, December 1st in Arlington, Virginia. You can register for symposium and view the program agenda at the link shown here. Finally, I would like to remind you that a copy of the presentation of today's session can be downloaded from our webinar webpage. We would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at the end of the webcast. I hope you enjoy the webinar today. Thank you.
Thank you, Maya. And now it's my pleasure to introduce our first speaker, Dr. Isaac. Isaac is a scientist and subject matter expert in cold spray technology in the Manufacturing Science and Technology branch of the U.S. Army Research Laboratory. He provides technical direction to ARL's university and industry collaborators on cold spray research, ranging from fundamental to applied, and he leverages results to support ARL's cold spray projects. His research interests include cold spray of multi-phase materials, robotically enhanced cold spray, defect prediction and mitigation, and tool path planning for cold spray additive manufacturing. He received a doctoral degree in applied mathematics from the University of North Carolina in Chapel Hill. Isaac, please proceed.
Thank you, Jennifer. So today I will be presenting on an ESTCP project in which we developed and evaluated cold spray coatings for chrome and nickel plating replacement. So I'm going to start off my presentation today by going into the background on cold spray technology, what it is for those that are unfamiliar, why we wanted to use it for chrome and nickel plating alternatives, and some of the engineering challenges that we needed to overcome to make the technology work. Next, I'll be going into some selected key test results from the project. After that, I will be covering some of the key lessons that we learned on the project, and I hope to give you a roadmap for implementing cold spray at your facility. Then finally, I'll be going over the conclusions of the project. So let's start with the technology background. Cold spray is a technology for consolidating metal powder. It works by adding metal powder to a heated gas stream, which is carried through a supersonic nozzle that accelerates the metal particles to very high velocities between 500 and 1500 meters per second. At those high velocities, the metal particles undergo extreme plastic deformation when they hit another metal surface. And that extreme deformation allows those particles to bond to the metal surface and to build up a thick coating over time. Now we call this cold spray, but we're actually heating up the gas stream by as much as 900 degrees C. The reason we call it cold spray is because we keep the particles below their melting temperature. So when they impact the metal surface, they're in solid state. And the process is primarily kinetic energy driven as opposed to thermal energy driven. So the solid state nature of the process gives us certain advantages. Mainly, there's negligible thermal impact on the substrate, and we can build thick coatings with minimal porosity. Another advantage is that because we don't require a significant heat source, we can design nozzles that are small enough to fit inside inner diameters so that we can coat very long tubes on the inner diameter of the tube, and we can go down to about 2 inches inner diameter. So there's a lot of reasons why we would want to use cold spray for a chrome plating alternative. But one of the challenges is that chrome plating is a very high hardness material, and it can be challenging to get very high hardness cold spray coatings. The reason for that is because we need some plasticity in the solid state of the metal feedstock material so that we can successfully build up a dense coating. Traditionally, cold spray is focused on metal feedstocks, and cold spraying hard metals or ceramics requires additional engineering. So the way that we address that for this project is by using two-phase cold spray, in which we combined hard phase materials like ceramics with softer phase feedstocks. And the reason we do that is because we need the hard phase material to increase the bulk hardness of our deposit. And we need the soft phase material to give us the plasticity we need to successfully build a dense coating. So in a prior SERDP project, we evaluated a series of different combinations of hard phase and soft phase materials, as well as different methods of combining hard and soft phase materials. And those methods range from simple blending, in which you just take a hard phase and a soft phase feedstock powder and blend them. So your feedstock has two different types of powder particles. And that ranges all the way to agglomeration, such as through spray drying, where the process yields a single powder particle that contains both hard and soft phases. So the outcome of that SERDP program was a series of cold sprayable feedstock powders that are tailored to wear and impact protection applications. And we call those powders the WIP powders for short. 4 powders were down selected for further evaluation on the ESTCP program. WIP C1 and WIP C2 are chrome carbide based powders, and they're produced using simple blending. And I do want to note that these powders contain chrome chemistry, but it's trivalent chrome instead of hexavalent chrome. And we also had the WIP W1 and W2 powders, which are tungsten carbide based and are produced by spray drying, sintering, and granulation. All the powders are hexchrome free. All these whip powders have a volume percent of hard phase that is over 50%. And yet we were still able to produce very dense cold spray coatings with these materials. And having that hard phase volume percent so high was important because that gives us the hardness that we need from the bulk deposit. We also developed cold spray processes, or what I call recipes, for each of these materials. And in some cases, we develop multiple recipes per material. So for C1 and C2, we have both helium and nitrogen spray gas recipes. And we also have miniature nozzle recipes, which allow the process to be done inside of the diameter of a tube. So altogether, 7 recipes were down selected for evaluation on the ESTCP project. The objective of the ESTCP project was to evaluate each of these 7 recipes for a wide range of tests with the ultimate end goal of substantiating the technology for real DoD applications. A second objective of the project was to develop or stand up cold spray capability at DoD overhaul facilities, and at those same facilities demonstrate our cold spray technology on real DoD chrome plated parts to further substantiate the technology. All right, so at this time, I will go into some of the key test results that we found on the project. The first is micrographs. So what we were looking for with micrographs is a dense coating with minimal porosity. What we found is that all of our coatings met that criteria. Another interesting thing to point out about these micrographs is the difference between the methods of combination. So remember, the C1 and C2 feedstocks are produced by blending, while the W1 and W2 feedstocks are produced by spray drying and sintering. And you can see that in the microstructure. So with the C1 and C2 micrographs, you can actually see what were once the hard phase particles that are now embedded in a soft phase matrix. With the WIP W1 and W2 coatings, you can still make out 2 distinct phases, but the characteristic size of the phases is smaller because those phases were agglomerated within a single powder particle. So what we found in general is that W1 and W2 coatings are slightly more robust than the C1 and C2 coatings because we think the coatings are more homogeneous. But there is a slight increase in cost from the W1 and W2 feedstocks because of the additional steps in the manufacturing process. The next thing that we evaluated is a shear adhesion strength, and we evaluated this using lug shear testing. We also evaluated our coatings on a number of different substrate combinations. What we found across the board is that all of our coatings and substrate combinations had at least 20 KSI yield strength. Now, there isn't really a comparison for chrome plating because with chrome plating, you can't do lug shear testing because that testing requires you to build up enough thickness of material that you can machine a lug, and you can't do that with chrome plating. But to provide some context here, you can compare these coatings to thermal spray coatings. And in thermal spray, there's something called an ASTM C633 glued bond bar test that's used as a pass-fail criteria for thermal spray coatings. And the pass criteria for that test is a glue failure. The glue is only as strong as about 10 KSI in tensile strength. So basically the passing criteria for a thermal spray coating is at least 10 KSI tensile strength. What we evaluated was the shear strength, which is typically about half of the tensile strength for a material. And we found that all of our shear strengths were at least 20 KSI, which is twice the pass-fail criteria for a thermal spray coating. Next is micro hardness. So there's some trends that we can observe in the micro hardness data. First, the feedstock material has a significant effect on the resulting hardness of the deposit. So we saw that C1 has the lowest average hardness, C2 has something in the middle, and W1 and W2 have the highest overall hardness. We can also see that there's a difference in hardness between the helium and nitrogen versions of each feedstock. So we typically see the helium version is slightly higher hardness than the nitrogen version. But that's of secondary importance to the feedstock itself. Unfortunately, none of our coatings had equal or better hardness as typical chrome plating values, but the W1 and W2 coatings do come close in hardness. However, we don't see this as being a disqualification of cold spray because hardness isn't the only metric that is important. And in fact, we found that in many cases, our cold spray coatings have better wear protection than chrome plating. So that brings us to the next slide. We did a variety of different types of wear testing, and this is just one example of wear testing that we did. So this is a block-on ring wear test where we had 52-100 steel rings that rubbed up against cold spray coated blocks and a filtered 2190 TEP lubricant. We did that test for all the cold spray coatings and also a chrome plated sample so we could have a direct comparison. What we found is that all of the coatings except one had better wear performance than chrome plating. The one coating that didn't was the WIP C2 sprayed with nitrogen. And in particular, the WIP W1 coatings had much better wear resistance than the chrome plating. So this is something that we saw with most wear testing we did. There were some cold spray coatings that were worse than chrome, but a large number overall of the cold spray coatings had better wear resistance than chrome in different loading situations. We also evaluated corrosion, and on this slide I'm showing salt fog corrosion results. So in this test we exposed the cold spray samples to salt fog for 40 days. We also, for comparison, tested an uncoated 4340 substrate. What we found is that the mass loss of every coating was negligible compared to an uncoated 4340 substrate. However, when we look at the micrographs of those samples after 40 days, we did see that the WIP W1 coating had significant porosity that had formed, which would indicate that the W1 would not have great corrosion resistance and may need additional protection. However, all the other WIP C coatings did not have any pitting after 40 days exposure. So to conclude the joint test protocol results, there's a few main takeaways we can make. First, for helium versus nitrogen spray gas, helium generally yields better mechanical performance and minor differences in non-mechanical performance. But we saw that the difference between helium and nitrogen was minor compared to the differences between feedstocks. So likely for these type of applications, you should be able to get away using nitrogen gas, which is much cheaper than helium gas, by choosing an appropriate feedstock material. The second observation, when we compare cold spray to chrome plating, we found that chrome plating has higher hardness than our cold spray coatings, but our coatings were shown to have better wear resistance in many different loading situations. Finally, for corrosion, we found that WIP-W may not be the best solution for corrosion protection, or it requires additional protection. All right, next I'm going to go into some of the lessons that we learned during this project and try to communicate those to you in a way that would be useful if you're trying to set up a cold spray capability at your facility. So we did demonstrate the technology on real DoD applications under this project, but I can't go into the details of those applications in a public forum. So instead, I put together this table which shows the range of applications and transitions that we've worked on. And so we've used almost the entire range of WIP materials. And we've also looked at both chrome outer diameter and inner diameter applications, as well as nickel outer diameter applications. We also have worked on applications for chrome and nickel replacement that use other materials besides just the WIP materials. So in most cases that you see here, these are partnered with a DoD facility, which has its own organic cold spray capability. And in most cases, that facility comes to us with a problem, and we work with them to solve that problem using a cold spray solution. And in many cases, we have helped those facilities with standing up their cold spray capabilities. So through all those efforts, we've learned some very valuable lessons. First, in almost every case of a cold spray system being installed at a facility, we've seen delays associated with getting approvals for safety related things from approval authorities. So what I recommend for that is, when you are writing up a contract with a cold spray vendor to provide cold spray equipment, make sure you include in the contract language that requires them to support your approval activities. Cold spray vendors have experience with this. They have data to back up their equipment and seek approval from authorities. But you need to protect yourself and just make sure that they're contractually obligated to provide that support. The next thing, I have seen cold spray operations completely derailed by employee turnover. So what I recommend for that is, if you're going to operate a cold spray facility, have a team of at least 2 dedicated operators. That way, if one operator leaves for another job, you have the old operator that can train the next person. And the reason that's important is because cold spray is still relatively new technology, and it's not easy to find people on the job market that have prior cold spray experience. So more than likely, anyone you bring in is going to be trained on the job. I also recommend to make sure that your team is dedicated to cold spray, as opposed to working on cold spray maybe 10% of the time, because if they're only working on it a small fraction of the time, then they're going to grow rusty and forget how to do things. So maintain a team that's working on it for most of their time, and you'll be successful. The next lesson is that surface finishing is required for almost every cold spray application. Some people don't realize that the typical surface finish of a cold spray is like sandpaper, and there's very few applications in which you can get away with leaving the as sprayed finish. So it typically requires either a machine finish or a grinding finish before it can be used in application. So keep that in mind as you develop applications, that you need to have the equipment necessary to finish the relevant geometry. So if that's an inner diameter, then you need to have equipment capable of finishing the entire cold spray surface. And finally, there's not a single one size fits all cold spray solution to every problem. The feedstock and gas selection are very application dependent. And that brings me to this next slide. So under the ESTCP project, we developed a large body of data. And we also developed a cold spray cost model, which should be useful in the future for determining the optimal feedstock selection for a given application. So the cost model is based on a cost per volume. The cost of cold spray scales very linearly with the volume of spray material. So you calculate the spray volume by taking the surface area and multiplying it by the required thickness, and then you would just get the cost by multiplying that volume by the cost per volume, which is shown here in the plot. And that can be used to estimate your costs. It doesn't account for all things. It doesn't account for labor or one-time capital equipment costs, but it should give you a good estimate of how much it will cost on a per part basis. And so as an example here, I plotted the cost per volumes of each of the WIP materials against the average hardness of those materials, which provides you an idea of where the different materials stand in terms of cost and performance. If you look at it this way, WIP W2 sprayed with nitrogen looks like the best all-around combination of cost and hardness. But it's important to keep in mind that hardness is not the only metric that is relevant to an application. So when you're deciding what feedstock to use for an application, you're not just going to be using hardness to make that determination. You're going to be looking at wear, performance, corrosion, and a whole variety of factors. All right, so this time I'll go into my conclusions. So what we found in this project is that cold spray can be utilized effectively in some applications in which chrome is currently utilized. Optimal feedstock and spray gas are application dependent, and the final report that we wrote should provide a roadmap for determining or at least getting a head start on what feedstock you need for a given application. Two-phase feedstocks can be tailored for unique engineering requirements, and operator training and workforce retention are critical to success. This project has been beneficial to the Department of Defense. So cold spray offers another tool for replacing chrome or nickel plating. We've shown that cold spray is effective for DoD applications in which chrome plating is currently used. In particular, inner diameter coatings and thermally sensitive substrates seem to be the most ideal applications. And beyond chrome plating alternatives, we've also shown that the WIP materials are effective for non-chrome applications too. For example, repair of steel armor. So overall, we developed a large body of data that provides a roadmap to potential users to determine what feedstock they need for given applications. We also encourage you to reach out to me or any of my colleagues at ARL if you need guidance on developing an application. I want to acknowledge Dr. Caitlin Wald and Rufus Adams for Solvus Global. for developing much of the content that is in these slides. And here's my contact information in case you have any subsequent questions. So thank you.
Thank you very much, Isaac. And at this time, I want to remind our audience that you can submit questions for Isaac using the Q&A box on the Zoom platform. And we have received a number of questions. Isaac, the first one is from the Naval Air Warfare Center. How long does it take to achieve the desired coating thickness compared to plating?
Yep, so that is very dependent on the surface area that you need to coat. What I would say is that if you're comparing it to plating, you know, plating, you're kind of building up the thickness across the entire area. Whereas with cold spray, you're only building up a small area per time. So it's difficult to, it really is dependent on the size of the application that you have. What I would say is that if you have something that is, you know, maybe a surface area of around 20 square inches, then you'd be looking at somewhere on the order of around 10 minutes to build a thickness of around 3 thousandths. But that's just a quick estimate.
Okay, great, thank you. Next, a question from the Army Research Lab. Is the cold spray performed in a vacuum, in inert gas, or air at standard temperature and pressure?
It's performed in air at standard temperature and pressure. Okay,
great. You talked about using trivalent chromium, and when that is used, is there any concern about oxidation into hexavalent chromium?
No, I would say that there is not any concern because cold spray is a relatively low temperature process. So the feedstock powders are carried from the powder feeder to the cold spray nozzle in either helium or nitrogen gas. And the only point at which they might be exposed to air or oxygen is in the short time at which they are outside the nozzle. And what we've seen with most applications is that there's very minimal pickup of oxygen from feedstock materials to the final deposits, even when we're spraying in an air environment. And the reason for that is because even after materials are outside the nozzle, they're still kind of shielded by the cold spray carrier gas, whether it be helium or nitrogen. And since it's also a relatively low temperature process, then you're not going to have much pickup of oxygen during that time.
Okay, great to know. Thank you. We had a question about which cold spray systems were used. Can you say anything about the systems used?
Yeah, for all this testing, we use VRC cold spray systems, either Gen 3, VRC Gen 3 or VRC Raptor cold spray systems.
Okay. Great, thanks. The next question is about slide 27, where those images were shown. And the question is, what are the spherical particles at the interface of the W1 and the W2 microstructures there?
Yes, so for the WIP W1 and W2 coatings, actually for all the coatings, we use a bond layer. So the first layer of material is different from the subsequent layers of material. And the bond layer actually is a blended feedstock that's very similar to WIP C1 and WIP C2. So it's not, the bond layer is not an agglomerated feedstock, and that's why you see those spherical particles that are only at the interface. The purpose of that bond layer is to improve the adhesion strength of the material.
Okay, great, thank you. The next question is from, again, the Naval Research Lab. What chrome or nickel coating applications are most suitable for replacement by cold spray? What are the target applications?
Yeah, so I think that to answer that question, you have to be cognizant of the other technologies that are out there for chrome plating alternatives. So you have thermal spray technologies, and you also have non-hex chrome plating technologies. So the niches that I see for cold spray are inner diameter coatings and applications with thermally sensitive substrates, because those are applications that may not be suitable for thermal spray. And then when it comes to chemical plating, masking can become an issue for chemical plating, whereas cold spray does require some masking, but only in the areas near the, near where the cold spray is going to be applied. And it's only required if you need to protect some other area on the part. So it doesn't have as much masking requirements, and that can be an advantage if you have smaller parts or one-offs where you don't have the time to develop masking for a specific one-off part. Over.
Thanks. Next, were you able to evaluate fatigue on these candidates?
Yes, we did evaluate fatigue for these, and the testing wasn't done before the slides were drafted, so it didn't make it into the slides, but I can summarize the results that the testing we did was 4340 substrates with WIP C1 and WIP C2 coatings, and also a baseline of chrome plating coating. We didn't test W1 or W2 because we ran out of time and resources. But what we found is that there was very little difference in the fatigue life of our samples when comparing the C1, C2, and chrome plating. And we think the reason for that is because the coatings were very thin relative to the cross-sectional area of the samples. So most of the fatigue life was dominated by the 4340 steel. But it does tell us that the coatings when thin, don't seem to have a very significant effect on the overall fatigue life.
Okay, great, thank you. We've had a couple of questions about the requirements for the feedstocks and the powder sizes. Is there a powder size below which cold spray cannot support its application? And are there any other requirements?
Yes, so cold spray feedstocks typically need to be in the range of about 10 to 50 microns. If you go much below 10 microns, at that point, the electromagnetic forces between particles overcomes the size of the particles, so that the particles tend to stick together, and then you don't get very good flowability of the powder, so it doesn't feed very well in the process. And then you also have particles that are sticking together during the process. So that's the main reason why we need particles that are at least about 10 microns. And then on the upper size, if you go much above 50 microns, then you don't accelerate the particle fast enough to significantly deform during the process. So you don't get a very good quality coating. The whip coatings that we developed are all compliant with a cold spray powder mil spec powder standard. So there has been a cold spray mil spec that outlines requirements such as the size distribution and other requirements for powder. Over.
Okay. Thank you, Isaac. We have one last question for you. This is from the Naval Air Warfare Center. Did you characterize the thermal expansion properties of cold spray compared to platings? And the question refers or is asking from the perspective of high temperature cycling applications.
No, we did not evaluate the thermal expansion of these coatings. We have evaluated coatings for high temperature cycling, but not these whip coatings.
Okay.
Over.
Sounds good. All right. Well, Isaac, thank you for the presentation and answering questions. And as a reminder to our audience, we'll have Isaac come back at the end of the webinar to answer a couple more questions. Now we'll move to the second presentation for today, which will be delivered by two speakers. The first is Mr. Greg Liscombe, a technology development and hazardous material reduction engineer with the Air Force Sustainment Center Engineering Directorate, which is located at Warner Robins Air Logistics Complex. Greg manages multiple technology development and demonstration validation projects with a focus on the hazardous material reduction during aircraft maintenance processes. He received a bachelor's degree in industrial engineering from Virginia Tech and a master's degree in business administration from Florida Tech. And the second speaker today is Mr. Casey Jones, the materials and processes manager at ES3's Southeast operations in Warner Robins, Georgia. And Casey has been working in corrosion prevention and control in the defense aerospace industry for 13 years. He oversees and develops new projects related to organic and inorganic coating development, hazardous material removal from the aerospace industry, sustainable methodologies for coatings, and being associated with technology insertion into defense applications. He holds a Bachelor of Science in Chemical and Biomolecular Engineering from the Georgia Institute of Technology, and a master's degree in business administration from Mercer University. So Greg, please go ahead and kick us off.
Hello all, this is Greg Liscombe. Thank you all for attending this event and being a part of this presentation. It's an honor to speak in front of you and to be a part of this and to work with Casey Jones and ES3. Again, my name is Greg Liscombe. I am an industrial engineer supporting Warner Robins Air Logistics Complex. We are an ALC, and we essentially support aircraft maintenance, working on C5, C-130, F-15, and other aircraft. Air logistics complexes are in the Air Force. We also work with fleet readiness centers and Army depots. So for today, I'm going to go over a couple of things with this project related to this demonstration validation project. We'll go over some of these technical objectives, a lot of the work accomplished during the project. So the testing, training, equipment installation that was part of the capital investment program, the technology transfer opportunities to other locations, and then we'll wrap it up with some conclusions and benefits. All right, so this project, demonstration validation of LHE, alkaline zinc-nickel electroplating, at the Advanced Metal Finishing Facility, or the AMFF. We'll start using AMFF from here on out. That facility was constructed about 12, 13 years ago. So a relatively new plating facility on Robins Air Force Base, supporting aircraft maintenance. And it's a new zinc nickel plating line going in there. So it's a great great to see new equipment and essentially taking technologies and installing equipment and demonstrating that equipment. The ESTCP project is demonstrating and validating that rack plating process and completing all the testing necessary to accept that plating line. So it's great to see that, especially with the government engineers. They are working production, they are supporting aircraft maintenance production. So to qualify a new line is a lot of work, and to have ES3 and to have ESTCP fund that effort is a huge help to all of us here at Warner Robins. All right, so a little bit more here, project progress. We are nearly complete on this plating line. It is a matter of the next few days or even into next week, I believe. We should have government acceptance of that plating line. We had a couple short delays and that kind of stalled out the DEMVAL project as well. But it's going really well, and we should see that plating line accepted, I would say, by the end of the month at the latest. And we should, we've already kind of begun supporting that plating line with the DEMVAL. We've had anodes designed and fabricated for a few parts, and essentially starting that qualification process as well. So we're looking at in 2023, we are working to start actually demonstrating and validating on some of those aircraft components early next year as well. So I think we're going to have a full operational capability about the ending of this ESTCP project as well. So it's should be seeing this. All right, next slide. Sorry. So here's a couple of shots just to give you a little bit more view. That's the zinc-nickel plating line at the AMFF. Some of those tanks, and there's just an example of an electroplated part on LHE zinc-nickel from ES3's design and fabricated conformal anode. So you're going to see a lot of similarities with the tanks and the components that we're going to just looking at, and we're fabricating the anodes and plating the part. All right, so a few more key points. This is by no means a brand new technology. It's been around for a little bit. I believe some of the old SIBR topics go back to 2007, 2008. So it has been approved and is a preferred alternative to cadmium per TO 11691. And that's what we're here to do. We are here to eliminate cadmium plating on our aircraft components. We're here to eliminate cadmium exposure for our maintenance employees, everybody working on those aircraft, working on sheet metal and components that are exposing them to cadmium. Not only is it a preferred alternative for ESO alternatives, but it does provide superior corrosion, abrasion resistance, and it is that reduced use of carcinogens for our workforce. That plating line, it says completely installed. We're right there. I think we're a matter of a week or two away here. And CMXG, Commodities Maintenance Group, is they essentially operate that AMFF on Robins. So they've approved it. They're about to accept it. We are looking at accepting parts, and essentially the next phase is to begin ramping up our workload and to start identifying parts. And ES3 has begun that process and looking at all the weapon systems that we have on Robins and start identifying some of those maybe low-hanging fruit that we can start plating on a regular basis. The training is drafted and it should be provided in November, and the manuals have been delivered as well. And sorry if you're not picking up audio a little bit. I'll try to speak a little bit clearer and a little bit louder here. Technical objectives for this, again, a little bit repetitive here, but let's just focus on a couple things here. Safety of flight and airworthiness, and we want an environmentally friendly alternative to cadmium plating. That's what we're going with here. That ES3 plating process is what we're, that's what we're working on. We are working directly with ES3, Casey Jones, Jay Randolph and their group over there right outside the gate outside of Robins Air Force Base. So it's great to work with them. This combined effort, it will validate rack plating process. So we will be pushing it through an automated system on a rack plating process. And it's a great facility. If you're in the area, please contact me if you're open for a tour. I love showing off that facility. It's pretty nice. And then the last thing there is that conducting the testing necessary for the acceptance of the plating line. And that is what's going to go on through early spring. Next slide. All right, so I'd like to welcome Casey Jones. He will provide a little bit more of the background and some of the tasks that we accomplished with this ESTCP project. Casey, are you online?
Greg, can you hear me?
Yes, sir, I can hear you.
All right, awesome. Yeah, like Greg said, I'm Casey Jones, Materials and Processes Manager here at ES3. I'm glad to present to you guys. So just going right into the slides for the equipment installation. So this was a large plating line. We added 7 tanks. Typically, they're around 400 to 500 gallons. All of these are 3,000 gallons. So dimensions of roughly 6 foot by 6 foot by 12 foot deep. The extra depth was to allow for overflow plating from Hill Air Force Base in the event their zinc-nickel line that we installed several years ago was down. So it's 7 tanks added to line 3 at the AMFF. I'll be going into some of these other things in more detail. We've taken care of all of the tank installation. Like Greg said, all of the CIP funded work is essentially finished. And then I'll start talking about some of the quality control measures for we're qualifying this line in accordance with that military detail 32648, which is what Hill Air Force Base uses. You can go on to slide 53, Greg. So the plating line qualification, what we've been doing the last several weeks is chemical analysis. We've actually used sort of a round robin trifold approach where we have done the analysis about 5 times now. The chemical analysis flight at Robins Air Force Base that's going to be required to keep this in check throughout its duration has performed some analyses, and DIPSL that manufactures chemicals, the IZC17 Plus and 264 that you saw, has also performed some analysis of this. So some slight differences from one lab to the next, but we're very, very close. And we should be getting all of that in check where we can start plating some of these other coupons that you see in the 4 remaining sub-bullets, all of which are quality control tests in accordance with that military detail 32648. Qualification of the chemical is already completed. New chemicals would have to go through the full qualification requiring fatigue testing and stuff like that. But the DIPSL chemical is the only product on the qualified products list for that. So that's why you see joint test protocol is not required. This is just the routine quality assurance testing that has to be done on a monthly basis. You can go on to slide 54, Greg. This just shows, sorry about the imaging here, but this just shows a couple of the tests that we've ran. This is us keeping our plating line in check. We're currently performing plating for the 571st and 402nd at Robins Air Force Base. One of the tests that we have to perform is the ASTM 519 HE testing. You can see 4 coupons there all threaded together and loaded. That's really precisely machined coupons that have a specific knot fracture strength. We have to purchase those coupons and certifications. So we'll be plating 8 of those next week, 4 for our laboratory to qualify it, and then 4 for the AMFF's facility to qualify it as well. And then the B117, most of you guys I'm sure are familiar with that, but 96 hours is part of the routine quality assurance testing as part of that. We've already performed that once, but we'll be performing it again once all three labs are in agreement that the plating solution is all within specification. You can go on to slide 55, Greg. All right, so training. Actually got an email yesterday from some of the production supervisors. They're ready to start some training next week. I believe 8 a.m. Tuesday is what they proposed. We've developed 3 different types of training, already completed and submitted all of the slides. One of them is for engineering staff. That will be a good bit more in detail on sort of the analysis of manufacture of these conforming anodes. They're interested in licensing our software, Venus, which I'll go into detail about a bit later. Operator training is going to discuss more about the different programs and recipes that they would need to use for a given part. And then maintenance training would talk more to solution maintenance and keeping the line in quality, as well as how often to change filters and things like that. You can go on to slide 56, Greg. So some of the analysis that we performed already and that they performed on base, titrations, which would be done more for the molecular components like sodium carbonates, and then all of the elemental analysis is typically done, at least at ES3, with the AA atomic absorption spectroscopy. Then after everything is in quality from a chemical analysis standpoint, we'll perform the test that you see in that last bullet there. Next slide, Greg, 57. All right, so after everything has been qualified, meaning all of the testing that you've seen has been completed, we've gotten 3 different components. We're trying to make this as tri-service as possible. So the C5 horizontal stabilizer pivot shaft, you'll see some pictures of that a bit later, is one of the demonstration validation components. The C-130 used by both the Navy and the Air Force, the propeller barrel hub, pretty complicated design for that. So we had to do a good bit more work from the simulation and analysis, design and manufacture of the conforming anode for that, and the H-60 flange assembly, which would be a tri-service part. We're also doing some work for Corpus Christi Army Depot, looking at qualifying their upcoming plating line with all the fatigue testing and stuff that we're doing now. They just have different design requirements from a qualification standpoint. So you'll see some of these conforming anodes in follow-on slides. And then at the end there, at the bottom, you see the list that we compiled of all of these parts. We've identified, I believe, close to 200 parts. I think it's a little bit over 180 different parts on multiple different platforms, but you'll see that on some later slides. You go on to slide 58, Greg. This just shows how conforming anodes are designed. So at the top, you'll see just a 3D solid model of the C-130 propeller barrel hub. The gray area, both on the left there, that barrel itself, and then the inside of the barrel is not zinc-nickel coated. So that would be masked during the plating process. It's HBOF or hard chrome plated. And that's what you also see in purple in the next two images, things that are masked and things that are not plated. So after running the initial Venus analysis, which would be your second line here, that means no conforming anodes have been put in place. It's just plating with the tank anodes that are on the sides of the tank. You can see the different thicknesses that you're going to get in the blue, green, and red areas. So the requirement for the specification is to be between that 0.5 to 0.8, which is the class 1 thickness requirement. After you place conforming anodes, theoretical conforming anodes in space, and then rerun the evaluation, you can see that all of that blue area goes away, and then everything is held together using fixtures. So we use 3 or 4 stainless steel primarily to hold nickel 200, which would be the like the dark red components that you see there, to make sure it plates in all of those areas that would be highly underplated, if plated at all, in the blue shading there. Going to the next slide, 59, Greg. Another component that we looked at is the H60 flange assembly. Like I said, that's a tri-service component. You can see a bit more simpler. So the design was simpler, but the blue area would be underplated. The entire inside of it is not going to get any plating at all, because when this is dropped in solution, all of your tank anodes would be on the outside of the part. So you can expect almost no plating on the inside. So we put a nickel rod down on the inside of that and then design. You'll see the fixture in a bit, but that plates everything theoretically very evenly. And you'll see where we plated this here at ES3's Georgia Technical Operations Facility in Warner Robins, Georgia, and everything plated very well. So we're going to do the same demonstration validation there at the AMFF as soon as we get everything in spec. Slide 60, Greg. All right, so the phase 1 test has been a 4-phase effort. We've completed all of that. We're currently, phase 1 would be the design of it and actually getting all of the 3 parts. Phase 2 was the build of the parts as far as the conforming anode fixtures and developing technique sheets, which is essentially a work package for how you assemble and disassemble, reassemble, etc. the conforming anode around the part. But all of those have been provided. We'll update those with the final design. You can go to the next slide, slide 61, Greg. This just shows the test plating. The next 3 slides are going to show the test plating of the part. So you can see on the left, you sort of start at the design phase. Your pink would be things that's covered in masking stainless steel that holds the anodic portion, the dark red, and you can see dark red in the middle there, which is the nickel 200, and the blue would be on the cathodic side. Before we plastisol these, which we see everything masked, we'll do a test plate, make sure everything plates properly within spec, 0.5 to 0.8 for class 1, 0.3 to 0.6 for class 2 in accordance with that 32648 specification. So now that we've done the test plating, these anodes have been finalized. They've been adapted to fit the swivel rocker feature and flight bar there at Robins Air Force Base. So in the middle, you see the test plating, and then on the right, you can see nice even plating all across there on the far right picture. You can go to the next slide. So this is the C5 horizontal stabilizer pivot shaft. You can see in the middle picture that we've got part of it masked off. That's either hard chrome or HVF plated, depending on where it's at in its life cycle. Again, the picture on the left just shows where the conforming anodes are at. Without those nickel rods in the center, you would not get any plating on the inside. So this is just required in order to get nice even plating in accordance with that specification. You can see the fully plated part on the right after it's gone through, everything plated nice and evenly. We'll demonstrate that same thing once we go to perform that dim valve. The last slide just shows one of the more complicated parts. We've already seen this, but this is the C130 propeller barrel hub. Like I said, the barrel itself is masked off. Everything else gets zinc nickel plated. So that's what you see here on slide 63. Going to the next slide. So these are just some examples of different parts that have been identified. Every month we do candidate parts list and send that out. What you see in the sort of peach color are parts that we are currently on contract under an IDIQ contract with the Robins 571st production, things that we're currently plating for them, but they'll be able to plate that as soon as we open this line up organically in-house. Things that are currently plated at Hill Air Force Base are shown in a tan color. Those would be things that could go to Robins Air Force Base for overflow workload, or in the event of plating lines down at Hill Air Force Base. And all of the others are candidate parts that probably currently get your cadmium plating, but can be zinc nickel plated as soon as the line is up and running. You can go to the next slide. This just shows you an example of the technique sheets. These will be updated since the meshing feature with the chain that we use for plating here at our line is very different from the automated line at Robins Air Force Base AMFF. That allows the workers to stay away from the chemicals the entire time, except for when adding or removing chemical. So everything's fully automated at that AMFF. But these are just some of the features of the technique sheets. This is some of the things we'll go through when we perform the training, and then we've already provided these, but shows the end users how they assemble everything, make sure everything's tight, make sure there won't be any arcing, and those types of things. You can go to the next slide. So these are just the quality control coupons we intend on plating next week. The testing for them will go quickly. The top left of the picture are the bend to break adhesion coupons. The notch 1A1 from the ASTM F519 specification of the hydrogen embrittlement coupons, and then the corrosion coupons that will run through ASTM V117 testing. So we're going to plate duplicates of everything at Robins Air Force Base request by the 402nd so that they can perform the testing, we can perform the testing, and then we'll get double validity, essentially, that everything is plating as it should, and we're getting the same result. You can go on to the next slide. This is just some more of the candidate parts. We've got them on C5, C130, F15. I think we've identified some C17 parts. B22 and H1 came out of Cherry Point, I think, FRC East. So a lot of the bases that still do not have zinc nickel plating capability, there's potential to do it at these this plating line here at Robins Air Force Base, especially with it being 12 foot deep, so it can take very large components with a 3,000 gallon tank. Next slide, Greg. That's it. Turn it back over to you. Thank you.
Yes, sir. Thank you, Casey. So again, great job by ES3, not only installing the equipment, but also working through this demonstration and validation effort. Just to give you all a little heads up on that, I mean, that's a combined $5.6 million contract. So 2 separate contracts totaling 5.6, and it's a great effort. And we hope to see really, really great things as the workload continues to ramp up. Let me see here. So a little bit more background on the equipment installation. I'm going to fly through these slides. That's just kind of showing you we had an existing line. We installed plating equipment, installed all the rebar, painted the floors, installed tanks, the shielding, got the Carbolux system installed, all the ventilation, the PCC and PLC installed, and that was one of the mods that we had recently that kind of slowed up the project. But yeah, everything was installed earlier this year. We had the ventilation installed as well. So it is essentially a completed, fully equipped system in the automated plating facility. So with that, now that we're wrapping up Warner Robins ALC, I love looking at how we can continue to technology and transfer this technology. I think the first candidate is our Army counterparts at Corpus Christi. We've been working with them. As you saw the part, that was one of the candidate parts as part of this DEMVAL. We will continue to work with them, ES3 as well, to modify their plating line, upgrade it, and potentially install a zinc nickel plating line over there as well. So if you're from the Army, you know, we'd love to chat with you about that. And if you're at Corpus Christi, you know, you're already familiar with that. So for Air Force, Hill Air Force Base has had a zinc nickel plating line for quite some time. They do landing gear components. I believe they might even be looking at a second line, but you know, they have had it for a while, and I really consider them the experts from the ALC perspective. And for the Navy, they have one both at Southeast and Southwest. I believe they may be looking at some additional lines, but that's the great thing to see here is proliferation of this technology going to multiple bases, multiple weapon systems and components. It's really starting to ramp up big time here. A couple more pictures on those plating lines. That's the North Island line, the Southeast Jacksonville line. and then some demvaling of some parts on the North Island line. So a little conclusion here, ES3 has completed. We'll consider the installation of the line complete itself, and the qualification is probably about 6 months from completion. So we're getting there. ES3 will perform that demval on those 3 components you saw that we had the conforming anodes and the test plating completed. And we're looking at having this training delivered and completed here in the next month as well. So benefits to the DoD, it's all about ESO. I'm going to take a minute to plug my organization and what we do. I'm part of a team for Air Force Sustainment Center. Each of our components has a hazmat reduction team. And we really meet with all of Air Force Materiel Command on hazmat reduction. So if you're in that world, we welcome you to join our meetings and to discuss various hazmat reduction concerns you may have. We have our own list of chemicals of concern, just like SERDP and ESTCP have, and we're working towards eliminating those as well. Other benefits of these systems, you've already heard from Casey. We have increased abrasion and corrosion resistance, decreased cost of maintenance, and decreased hazardous waste disposal, increased aircraft availability because it performs better than cadmium. So love to see these new systems go in, new technologies being installed. As an industrial engineer, it gives me great pride to do that. So this is acknowledgments. It's more just like the full product, the project team. Good shout out here to Clay Elliott from the C5 program. He was really one of the first people pushing this project and wanting to see zinc-nickel installed on his aircraft components. So Clay, big thanks to Clay and his team working with ES3 and on this program. All of ES3 as well. There, a whole team of engineers and scientists over there. Austin Walker and several commodities maintenance engineers have participated, and Nancy Likens from AMCOM, she's been supporting this project as well. So let's see. I will also mention one other thing. I work on plating line install, but I'm also working on dripless brush and other types of zinc nickel installation as well, and getting those processes up and running. So whether it's a plating line, whether it's a piece of equipment for dripless brush zinc nickel, or other areas of technology, that's what I'm working on implementing. So my area of expertise is not just zinc nickel, it's all hazmat reduction. I will be at the symposium in late November. I welcome you to discuss zinc nickel with me as well. But I will also be there talking about another technology, ultrasonic activated depaint for a methylene chloride alternative. So lots of good technologies coming in, and I welcome to discuss with anybody. Thank you all for your time. Appreciate it.
Wonderful. Thank you, both Greg and Casey. And we do have a few questions for you two. Greg, we'll start with you. It's a specific question about whether the zinc nickel plating can be used on aluminum. Greg, do you have any information on aluminum, or should we go to Casey?
Sorry about that. So we are working on the low strength and high strength steels. That's what we're focusing on for our components. We have not really focused too much on the aluminum plating from our perspective. I welcome Casey to add to that if there's additional sort of technology expansion towards aluminum and aluminum alloys. Casey, any input there?
Yeah, I mean, we've definitely done several years worth of studies on electrical connectors where black zinc nickel and some other products have been used, and have found that zinc nickel has outperformed cadmium and the black oxide zinc nickel and things like that. Primarily, it's been done on steel because it's a cadmium replacement, and cadmium is almost entirely used as a steel corrosion inhibitor. So like landing gear components and stuff like that. But yeah, I mean, zinc-nickel works on aluminum. It just has not been studied near as much because of the focus for getting away from cadmium, and most of the CAD being on steel fasteners and other aerospace steel components.
Okay. Understood. Thank you. Next, Greg, has the requirement for ventilation been reduced at all since the system is automated?
Well, that's a good question. You know, at the AMF itself, we have full ventilation systems there. I know it essentially covers whatever kind of PEL or regulatory requirement. Our workers are not in there in the plating area. It is a fully automated system. So I don't know. Sorry, I don't know how to answer your question completely there. Have we eliminated the need for ventilation? I don't think so. And that system is still needed, you know, to vent out everything from that area. But Casey, I welcome your input on that one as well.
Yeah, so we designed the system. It's called a push-pull system, where you're starting on one side of the tank, and 8 feet across the tank, you have suction. So you're pushing any fumes over to that. It works almost like a wind tunnel. Everything is closed off. You saw it in some of the pictures that were on Greg's slides, but it pushes any vapors over to that, and it mirrors the exact same thing that were on the other 8 lines at the AMFF. And like Greg said, there's no one that's present in the chemical line area while a part is being plated. They're in the operator area where you have a computer and you just can see where it's at in the process from one tank to the next. But ventilation is still required, same way as it is on all of the other lines there.
Okay, got it. Thanks. This next question for Greg is from the Missouri Department of Natural Resources. Do you have any idea how long it might take to phase out all of the cadmium platforms?
Yes, that's a great question, because that's the next step. You know, it's get the line up and running, get the line installed, have a few parts running. Oh, wow. And now the real work begins to start converting all those parts to zinc nickel plating. I personally think it will take several years to start moving all these. And one great example of that is, you know, we may need additional conforming anodes designed, additional, fixtures designed and fabricated. And each of those would be, whether that's in-house with our tool design folks or as a contract with ES3 to support that. I think that will take several years. This might be something we're working on for the next 5-10 years as we continue to upgrade our workload and start converting all those parts that Casey showed on a couple of those slides there. A lot of it comes down to how complicated they are. So we're going to try to do lowest hanging fruit first, get those easy ones. And I believe, some of those more complicated parts may be several years down the road. Over.
Okay, makes sense. Thank you. At this time, we'd like to bring our first speaker, Isaac, back on the line. There's a question that applies to both presentations, and that's: do you need pre-treatment of the surface before plating? Would the roughness or chemistry during corrosion create challenges for these applications? So, Isaac, we'll start with you, and the question more specifically for you is about cleaning and polishing for bonding with the cold spray feedstocks, for example.
Yeah, so I'm interpreting the question as surface preparation prior to cold spray as opposed to preparation after
Yes.
cold spray.
Correct, exactly.
Yes, so what we found is that you do need to have a clean surface. Generally with the repairs we're doing for chrome plating, those repairs are being done on part that was previously chrome plated. So the surface that we're spraying onto is a machine surface. And we don't require any additional preparations beyond the machining that's done. But you do need to have a clean surface. So obviously you don't want grit or dirt there. So we might do like an alcohol rinse and use like a Scotch-Brite pad to just remove any dirt. But that's about it. There's no significant requirements for the, if you have a machine surface. Over.
Thank you. Greg, pre-treatment of the surface.
I'm sorry, I missed that question. Is pre-treatment required for the zinc nickel plating line? Is that what you're asking?
Exactly, yes.
I'm not sure 100%. Casey, can you handle that one? When we have parts run through that system, I'm not sure exactly how much pre-treatment we do on them before they go in the basket and they go through that. And that's something we'll probably be learning here over the next couple of months as we run up this line. Casey?
Right. So usually if you get a part that may have been painted, you're going to strip off all of the paint. You're going to wash off any chemical stripper. Then you would take it, put it in a degreasing process to remove any residual grease in a parts washer. And then you can do like a grit blast preparation. I think we used about 60 grit for that, or 120 grit, excuse me. And then you can do a alkaline rinse wash after that. Alternatively, you can do a hydrochloric acid etch for just a few seconds prior to putting it in the zinc nickel tank as well.
Okay, great. And then we have one last question for Isaac. You had talked about recommendations for operators for the cold spray technology. Are there training resources available? And can you just reiterate that, please?
Yes, there are definitely training resources available, and the availability of those resources has really grown in the last couple years. You can get training from cold spray vendors themselves. There's also some cold spray laboratories and companies that have started offering 1 week in-person trainings. We at ARL, we're available. We've hosted visitors to go through informal training at our facility where they shadow us and watch, observe us setting up cold spray jobs. And, if you want more specific information, feel free to email me and I can give you a list of different training resources. Over.
Wonderful. Thank you. And thanks to all of our speakers today for the excellent presentations and answering the questions. Our next webinar in the series is on Thursday, November 2nd. That will be on efforts for managing populations of threatened and endangered species. Registration is open for this webinar as well as webinars through next year. So please visit the SERDP and ESTCP webinar webpage to register. Before we conclude, I'd like to remind you that both the audio and a copy of the slides from today will be archived on the webinar webpage in case you want to refer to them in the future. And that includes the contact information for the speakers. And we would appreciate it if at this time you could please take a moment to complete the survey that will pop up on your screen at this time. Thanks everyone very much.
Thank you all.